You know how sometimes you feel absolutely drained after a long study session or maybe a really tough run, and you think, ugh, I did so much work today.
Oh, absolutely. We all say that.
Right. But the thing is, in physics, that word work means something very, very specific. Often it's quite different from our everyday feeling of effort. So today we're digging into that exact physics definition and also its really important partners, energy and power. Welcome to your simple science summary on work, energy, and power. We've put this together specifically for you, our 17 and 18-year-old listeners in South Africa, especially as you gear up for your national senior certificate exams. And just so you know, everything we're covering, it comes straight from your CCAPES curriculum document and the official examination guidelines, so you're getting exactly what you need.
That's exactly right. And this section of mechanics, it's really fundamental because it kind of ties together how forces act on things, how that changes their motion, and crucially, how it changes their energy. Understanding these ideas isn't just about passing your exams, though that's important. It's actually vital for solving real-world problems.
Yep.
Think about designing machines or analyzing how athletes move or even understanding collisions. Ultimately, it helps us grasp why things happen the way they do in the physical world. It's all about, understanding how energy gets transferred and also the rate how fast that transfer happens.
Okay, let's unpack this work thing first then. So say I'm standing here pushing against this solid brick wall with all my might for like an hour. I'm sweating, I'm exhausted. Have I actually done any work in the physics sense? Because it definitely feels like I have.
Huh? That's a classic question, and it perfectly shows the difference, doesn't it, between everyday language and physics. Okay, so in physics, work is done by a force on an object only when that force actually causes the object to move, to be displaced in the direction of the force. So that brick wall, if it didn't move an inch, even with all your effort, nope, you've done zero physics work on the wall.
Wow. Okay, so effort alone isn't enough. There has to be movement caused by the force.
Exactly. Movement caused by the force in the direction of the force.
Hmm.
Work is a scalar quantity, remember, just magnitude, no direction, and we measure it in joules. Now, to actually calculate it, you need three things: the size or magnitude of the force, the magnitude of the displacement, how far it moved, and crucially, the angle between that force and the displacement. And here's the bit that often trips people up. Only the component of the force that's acting parallel to the direction of motion, actually does work.
Ah, okay. So if a force is acting sideways to the movement, it doesn't count.
Precisely. Think about carrying a heavy backpack across flat ground. Gravity's pulling down hard, right? Your shoulders might feel it.
Yeah, definitely.
But if you're moving horizontally, gravity is acting vertically downwards, perpendicular to your motion. So gravity is doing zero work on the backpack in the horizontal direction. Your effort is mainly just counteracting gravity vertically, not causing the horizontal movement itself.
Right. So it's not just about applying a force, it's about that force effectively causing motion in its own direction.
Okay.
Okay, that makes sense. So this leads to some really interesting points I saw in the guidelines. When can work actually be positive or negative
Yeah.
or even zero, like my wall example?
Yes, exactly. The relative direction is everything.
Hmm.
Positive work. That's when the force, or at least a component of it, acts in the same direction as the object's displacement. Like when you push a stalled car forward and it starts moving faster, your applied force does positive work. This adds energy to the car, to the system.
Okay, adding energy. Got it.
Negative work. This happens when the force acts opposite to the direction of displacement. The classic example is friction. Friction always opposes motion, right? So it does negative work on a sliding object.
Like slowing it down.
Exactly. Or think about applying the brakes in a car. The braking force opposes the car's motion, doing negative work. This removes mechanical energy from the system, usually turning it into heat.
Right, you can feel the brakes get hot sometimes.
Precisely. And zero work. We've hit on two cases. First, if the force is perpendicular to the displacement, like the normal force pushing up on a box sliding horizontally or gravity on that same box, neither force helps nor hinders the horizontal motion, so they do zero work horizontally. And the second case, as you found out with the wall, is if there's no displacement at all, no movement, no work done by that force. The guidelines even mention an example. If someone's pushing a trolley but they slip, so their force isn't actually applied over the distance the trolley moves during the slip, then that specific push didn't do work to cause that movement.
Okay, that's much clearer. Positive, negative, zero depends entirely on the angle between force and displacement.
And one more thing here. Network. This is just the total work done on an object by all the forces acting on it. You can calculate it in two ways, whichever is easier for the problem. Either find the work done by each individual force and add them all up, remembering positives and negatives,
Okay.
or you can first find the overall net force, the resultant force acting on the object, and then calculate the work done just by that single net force. You'll get the same answer either way.
So why is nailing this definition of work with all these details so important for us? Why start here?
Because work is, fundamentally, the measure of energy transfer due to a force. It's the absolute foundation. If you want to understand how energy changes in any physical system, from, I don't know, a simple pendulum swing to a complex engine, you have to start with a clear understanding of work. It's the bridge between forces and energy changes.
Right. Okay, so work is about transferring energy by applying a force over a distance. But what happens next? How does doing work actually change things, like an object's speed? I think that's where the work-energy theorem comes in. It sounds pretty important.
It is. It's a real cornerstone. The work-energy theorem is, well, incredibly powerful and surprisingly simple to state. It says that the net work done on an object, the total work by all forces, is exactly equal to the change in the object's kinetic energy.
Ah, kinetic energy. That's the energy of motion, right? Depends on mass and speed.
Exactly. Kinetic energy is 1/2 times mass times speed squared. So the theorem directly links the total work done to how much the object's speed changes. If you do positive net work, kinetic energy increases, meaning it speeds up. Negative net work, kinetic energy decreases, it slows down.
That seems really useful.
Oh, it is incredibly useful. It connects forces and displacement, which give you work, directly to changes in speed without necessarily needing to worry about acceleration or time explicitly. You can apply it to pretty much any situation you'll face. Objects moving horizontally, objects on ramps or inclined planes, whether there's friction involved or not. It just works. It simplifies a lot of problems.
Can you give an example, maybe one that's slightly less obvious, something we might see in an exam? What if something isn't changing speed?
Great question. Okay, think about a rescue helicopter, lifting a soldier straight up from the ground, but at a constant speed. The soldier's moving, there's displacement, forces are acting.
Right, tension pulling up, gravity pulling down, maybe some air resistance.
Exactly. But because the speed is constant, the soldier's kinetic energy isn't changing. The delta KE is 0. So, according to the work-energy theorem, if the change in kinetic energy is 0, the net work done on the soldier must also be 0.
Ah, even though work is being done by the tension pulling up and negative work by gravity.
Yes. The positive work done by the tension must be exactly balanced out by the negative work done by gravity and any air resistance. The total, the net work, adds up to 0, reflecting the constant speed. It tells you the forces are balanced in terms of their effect on the soldier's kinetic energy.
Okay, that's a neat application. So why is mastering this theorem so critical? You called it powerful.
Well, think of it like a shortcut, maybe even a bit of a cheat code for solving NSC problems sometimes. It lets you find things like the final speed of an object or how far it moved by focusing purely on the energy changes caused by the work done. You often don't need to go through all the steps of finding acceleration using Newton's laws and then using the equations of motion involving time. If you know the work done, or can calculate it, you can often jump straight to the change in kinetic energy and find the speed. It's a key problem-solving tool. Definitely one to get comfortable with.
Okay, work changes kinetic energy. That makes sense. But, we always hear about conservation of energy. Does energy just swap between kinetic and potential? What happens when things like friction are involved? Because friction seems to make energy just disappear.
That's a really important point, and yeah, it can be a bit confusing. The idea of conservation is central, but we need to be precise about when it applies fully. It hinges on the type of forces acting. We basically split forces into two categories. First, conservative forces. The work done by these forces when moving an object between 2 points depends only on the start and end points, not the path taken. Gravity is the perfect example. Lift a book straight up 1 meter, or wiggle it all over the place but end up 1 meter higher. The work done by gravity is the same.
Okay, path independent.
Right. And if you move an object in a closed loop, start and end at the same spot, the net work done by a conservative force is always 0. Gravity, the elastic force in an ideal spring, electrostatic forces, these are conservative. And importantly, we can associate a potential energy with conservative forces.
Like gravitational potential energy.
Exactly. Now, the other type, non-conservative forces. For these forces, the work done does depend on the path taken. Friction is the prime example here.
Ah, yeah. If you slide a box further across a rough floor, friction does more work.
Precisely. The longer the path, the more work friction does against the motion. Air resistance is another one. Applied forces, like you pushing something. Tension in a rope. These are typically non-conservative.
Okay, so two types of forces. How does this relate back to energy conservation?
Right. Here's the key principle. In an isolated system, meaning no energy enters or leaves, where only conservative forces are doing work, the total mechanical energy stays constant. Mechanical energy is just the sum of the kinetic energy and the potential energy, gravitational, elastic, etc. So in this ideal scenario, energy just converts between kinetic and potential forms, but the total amount remains the same. Think of a frictionless roller coaster.
Okay, so conservation mechanical energy only holds if only conservative forces are at play.
Yes, that's the crucial condition. But you asked about friction making energy disappear. It doesn't disappear, but it does get transformed. When non-conservative forces are present in doing work, mechanical energy is not conserved. The work done by these non-conservative forces, let's call it WNC, is exactly equal to the change in the total mechanical energy of the system.
So WNC equals the change in kinetic energy plus the change in potential energy.
Exactly right. WNC equals delta KE plus delta PE. Often, forces like friction do negative work, which means WNC is negative. This leads to a decrease in the total mechanical energy. That lost mechanical energy isn't truly lost. It's usually converted into other forms, like thermal energy heat.
Okay, that connects it to the real world. So friction doesn't destroy energy, it just turns mechanical energy into heat, usually.
That's the common outcome, yes. Think about that box sliding down a rough incline. Gravity, conservative, is doing positive work, trying to increase kinetic energy. Friction, non-conservative, is doing negative work, opposing the motion. The work done by friction reduces the total mechanical energy compared to if the slope were frictionless. Some of that initial potential energy gets turned into heat instead of just kinetic energy.
Right.
Or the example of a footballer sliding up a slope, friction does negative work, decreasing their mechanical energy until they stop.
So why is it so vital for us, for our exams and just understanding physics, to be able to distinguish these forces and know how they affect energy?
Because it allows you to analyze much more realistic situations. The real world is full of friction and air resistance and applied forces. Understanding non-conservative forces lets you track where the energy is going. It's fundamental for things like calculating energy efficiency, how much useful energy you get out compared to what you put in, and understanding how forces can either dissipate energy, like brakes, or add energy, like an engine, in practical machines and systems. It moves beyond ideal scenarios to how things actually work.
Okay, last big concept, power. Now, this isn't just about being strong, right? It feels like it's about how fast you do something. Like a tiny motor could eventually lift a huge weight, but a powerful crane lifts it quickly. Is that the idea?
That's exactly the idea. You've hit it perfectly. Power, in physics, is defined as the rate at which work is done, or equivalently, the rate at which energy is transferred or converted. So it's not just how much work you do, but how quickly you do it. Doing the same amount of work in half the time requires twice the power. It's a scalar quantity, like work, and its unit is the watt, W, named after James Watt. 1 watt means 1 joule of work done per second.
Okay, rate of doing work. How do we calculate it?
The most basic way is simply the work done, W, divided by the time interval, T, over which the work was done, so power equal WT. There's also another really useful formula, especially when things are moving at a constant velocity. If a constant force, F, is applied to an object moving at a constant average velocity, V, in the direction of the force, then the average power is simply the force multiplied by the average velocity, P equals FV.
Ah, okay. P equals F times V. That seems handy for constant speed situations.
It is very handy. You'll use both formulas depending on the problem.
So where does this show up in practice? What kind of problems or real-life examples use power?
Oh, power is everywhere. Think about a car accelerating. The engine needs to deliver power to increase the car's kinetic energy quickly. A more powerful engine can do that faster. Or consider a water pump, a very common type of exam problem. Lifting a certain mass of water to a certain height requires a specific amount of work against gravity. Doing that in a specific amount of time requires a certain power output from the pump. You'd use P or D, where W would be related to the change in gravitational potential energy, LNG.
Right, like pumping water out of a borehole.
Exactly. Even everyday things, running up a flight of stairs, involves power. You're doing work against gravity, lifting your mass from up a height, H. The faster you run up, less time, T, the greater your power output.
Makes sense. So why is understanding power necessary, beyond just calculating it for exams?
Well, power is intensely practical. Engineers need to design engines, motors, and machines with sufficient power to do the required job in the desired time. Athletes train to increase their power output for explosive movements. Even choosing appliances, a higher wattage microwave cooks faster, a more powerful vacuum cleaner might clean better. It's about the effectiveness of energy use over time. It's not just can the work be done, but how fast, which is often the critical factor in the real world.
Okay, let's quickly pull all that together then. We started with work, that specific physics idea of a force causing displacement in its direction, the foundation of energy transfer.
hmm
Then the work energy theorem, the direct link showing how the network done changes an object's kinetic energy, its motion.
Yep, when at delta KE.
Then we looked at conservative and non-conservative forces, understanding that mechanical energy is only conserved when only conservative forces do work, and how non-conservative forces like friction account for changes, usually losses, in mechanical energy by transforming it.
Crucial for real-world analysis. WNC equals delta KE plus delta PE.
And finally, power, which is all about the rate, how quickly work is done or energy is transferred, measured in watts.
Exactly. PET-FE equals FV for constant velocity.
Yeah.
Nicely summarized. And honestly, really getting these concepts down, the definitions, how they relate, and how to apply them in problems is going to be so helpful for your NSC physical sciences paper. Practice the problem types we've touched on, especially those involving inclines, friction, pumps. That's how you really nail it.
Absolutely. And maybe here's a final thought to leave you with. As you go out your day-to-day, maybe running for a taxi, charging your phone, even just walking up some stairs, try to spot the physics. How many examples of work being done, energy being transferred or transformed, and power being used can you actually identify around you right now? Understanding these principles really does give you a new way to see the world, revealing all those hidden forces and energy dynamics that are constantly at play.